a fast, scalable, and device-friendly public ledger designed to help IoT ecosystems become more trusted, autonomous, and valuable. Taraxa is founded by Stanford alumni with a focus on facilitating IoT data sharing and trading. The project's tech highlights include rapidly finalized DAG, concurrency inspired by CN, fuzzy sharding, trustless light nodes, and adaptive protocol, which will be introduced in the first speaker, CEO and founder of Taraxa, Stephen Poole. Let's welcome him.
This works. All right. It's really great to be here. I know I'm not scoring any points by saying I graduated from Stanford, but So today I'm here to talk about Taraxa and what we're sort of doing in the IoT space and types of applications that we're deploying. My talk will primarily focus on applications, and then I think Professor Herlihy will talk about a lot of the concurrency work, the research that he's been doing, and we're basing a lot of our actual innovations on his research. And then later we'll have a panel discussion. So we want to keep this entire meetup pretty informal. So if you hear something, you have some questions, you think I'm, spewing some bullshit, call me out, raise your hand and let me know. Okay. Cool. A quick introduction, right? So why are we really doing this? So I was a hardware engineer, so I studied electrical engineering. I always really liked hardware. My first startup was in IoT devices. IoT is something that is really near and dear to my heart, except it's an industry that grows really slowly. Right? Hardware it just grows really slowly. I can give you a very long laundry list of all the problems that we see in IoT that's holding it back from rapidly growing and scaling. But today I just want to talk about two specific problems, one short-term, one long-term. Okay. So the short-term problem is that as IoT devices or connected devices become deployed into all kinds of businesses, we're starting to see increasingly that a lot of business models actually depend on trust on device identities and device-generated data in order for those models to actually operate smoothly. And I'll talk about some of these cases during introduction to some of our applications. The longer-term pain point is this thing that everyone talks about with machine-to-machine economy, where we have increasingly larger and larger number of autonomous devices that are going to be operating. And as these devices scale in numbers, it's not going to be scalable, or from a security perspective, it's not going to be very secure to have a centralized governance system. But primarily, we're probably going to be talking about some of the short-term pain points. So what can blockchain really do for IoT devices, right? So number one, I think blockchain gives devices an identity, right? So right now, devices have identities, right? Apple knows where my iPhone is and whatever, right? But these identities are very siloed. This is another critical problem of IoT systems, is that there is no IoT industry. That doesn't exist. There's probably 200 million IoT industries, right? They're all locked into their little ecosystems that don't communicate or talk to each other, right? So this is actually an opportunity for devices themselves to actually gain an independent identity that is very much independent from their manufacturer or their ecosystem. So this is an interesting opportunity and a very interesting property for devices to actually have. The second thing is that they're able to actually own assets and be able to make economic decisions in terms of transacting resources. This is also very critical if devices are going to become economically independent rather than today they're just making very smart localized inferences, right? Like there's a cat or a rock. They can't do things like, well, my battery just right now, I need a software upgrade. Who do I go to, right? These type of decisions are right now centrally managed, and like we said before, as the number of devices increase exponentially, it's just not going to work out very well for a centralized governance model. So these are very interesting properties that I think blockchain can bring to devices, and in consequence enable some interesting business models and help devices actually really become a lot more valuable in our everyday work. So we actually built a public ledger. So Taraxa is a public ledger. We built the public ledger specifically because we want to gain the competence and expertise to actually design, implement, and adapt the infrastructure, right? So at the beginning, of the project, maybe back in late 2017 or early 2018, when we started thinking about entering the blockchain space, we had originally thought that, hey, it'd be really great to start building applications. But because the infrastructure was so immature and it was constantly changing, we saw that a lot of pure play application teams were hitting a lot of roadblocks, right? Because they didn't understand the infrastructure, they weren't able to communicate the value propositions of the technology, they were able to close the gap, they weren't able to change it to adapt it to their application needs. Their applications tend to fail, right? This is still an evolving infrastructure technology that we need to have expertise on, right? I can talk a little bit more about these towards the end, but we're very interested in horizontal concurrency across the network through a DAG topology. We're also very interested in vertical concurrency, which is allowing parallel processing of transactions on a single node, which Professor Herlihy will talk about. We have mechanisms to actually randomly assign block proposers and also assign transaction jurisdictions without coordination. We're in the process of doing research into trustless light nodes to make sure that light nodes are not so easily tricked by the phone nodes that are communicating with. And then we also want to be able to make our protocol relatively adaptive by having the technical parameters, things like block size, block proposer array, things like transaction jurisdictions, sections. All these kind of things should actually change according to real-time network conditions, right? They should not be decided, on Reddit through flame wars that last 2 to 3 years, right? They should just be well calculated and decided in real time. We just launched our testnet actually last weekend. It's not the most stable thing, but please, if you're interested, come check us out. We have instructions. We have a Discord discussion group specifically dedicated to the development of our testnet. So if you scan this, the instructions are all pinned in the Discord channel. So hope to see you online there. We are actually extremely committed to the Japanese market. So this is actually very interesting. We just recently published a book on blockchain with the Japanese government. It's called RIETI. It's the research branch of the Japanese METI, the Ministry of Economy, Technology, and Industry. So this is actually the first book published by the Japanese government on blockchain. It just hit the bookshelf on September 19th, and actually next week on October 7th, the METI will hold a symposium to actually announce this book. So this, in addition to all the other great work that we're doing in Japan, this actually gives us a lot of credibility when we're talking to large Japanese corporations. We can talk a bit more about this on the panel, but Japan just happens to be a very, very interesting space for us. We have lots of access and resources, and also in Japan, the legal status of cryptocurrencies and blockchain is very clear, unlike in the US where it's not so clear. And in other places in the world, quite similar. So it gives us a lot of certainty in the way that we actually work with our partners. We don't get asked a lot of questions about whether or not I'll go to jail when I work with you. Those topics don't come up in Japan. They do come up here in the US. They don't come up in Japan. So very, very interesting. All right. So the focus of the talk today is talking about some of the applications. So there's a big, big gap, right, between the technologists who have a good understanding of the technology and the business people who could potentially benefit from it, right? So everywhere I go to, I started off like thinking April, May this year, going around talking to businesses about the awesome technology we have, and all they want to ask me is, what is blockchain? Like, what is this blockchain thing that I keep hearing about, right? So the gap is very, very wide. It's very, very wide. It's very, very difficult to actually come up with archetypes or patterns where you can actually match the technological innovations with business problems they're able to solve. And that's something that we're actually constantly trying to do. So here today, we're going to talk about a few of the examples of applications that we actually work on and some of the patterns that we've actually discovered. They're evolving. They could be wrong. If you think they're wrong, let me know. We'd love to discuss that. Okay, so the first one. This is a very, very interesting case where trust of specific device identities and device data is critical to the success of a business model. So we're working with a very interesting company. They're probably one of the largest they're probably the largest arcade gaming machine leasing company in Japan. I didn't know such thing existed. So most of their business in the previous years have been focused in Japan, and their business model is very simple. They do a profit sharing model. So I'm the owner, I lease it to you. You tell me, and critically, you tell me how many times this machine has been used, then we split the profits, right? Very easy. And in Japan, apparently, everyone's very honest. They actually tell you, how many times this machine was used. So as this company started expanding their business to overseas, they suddenly discovered that, not everyone else in the world is so honest, right? They would lease it to other countries, and in the first month, yeah, no one's been playing this machine. Second month, no, nobody's been playing this machine. Third month, this machine sucks. No one's playing it. We want to keep it for a while, right? So how do we solve that problem, right? So the guy has over 10,000 orders from overseas market that he can figure out, how to fulfill. So what he can do is that he can say, well, get rid of this stupid profit sharing model, or just go with the fixed price model, right? You're just going to pay me X, whatever happens. And that's actually not a very good model. It's not a fair, it's not a fair economic model, because at any given moment, somebody's unhappy, right? Somebody's unhappy. It's also a very hard sell, right? When you initially approach a new customer, say, I don't even know this is an unproven machine, why am I paying this much money, right? So they want to get to the fair business model, which is the profit sharing model. So, simple solution, right? Just install a wireless module onto the machine that uploads how many times the machine has been played over to the cloud, and problem solved, right? Well, not really, because then there's the lessor, there's distributors, layer 1, layer 2 distributors, there's the final customer. They're going to be like, where are these numbers coming from? Just make them up on your Excel or what? Like, how do I know that these are the right numbers, right? So one of the things that we're proposing is very simple, is that as these devices, these wireless modules are capturing the data and then reporting them to the cloud, simultaneously they're hashing the data, putting a metadata around it, and then signing that data with a local signature. All of this is actually encoded into a secure element on the device, which is not very easily hackable, right? And then anchoring that bit of data into the blockchain, and that's it. That's all it does, right? So this is turning the blockchain into an audit trail, right? So what you can now believe is that, number one, this data actually did come from this specific device, right? Number two, after the data was generated, it hadn't been tampered with, right? So now you're not starting from, does this solve all your trust problem? No, it doesn't. It doesn't suddenly make people who are very distrustful of each other become best friends in the world. But you're not starting from zero anymore. You're saying, hey, we used to start from 0, but now we're starting from 50. Then we can talk a bit more about how we can build up that trust up to something manageable, so we can start trusting these numbers, right? So this is the first sort of pattern matching that we're seeing. This is something that we're also deploying with an engineering company, actually in Japan as well. So this is not written on the slide. There's a very large, publicly listed company in Japan. They're trying to build a hydroelectric power plant in Indonesia, in Sumatra, okay? And they're trying to get financing for this power plant. They're going to these Japanese banks, and they're saying, finance the project. The banks are like, I'm sorry, I can't. I'm not in Indonesia. I don't speak the language. We don't have people there. I don't know anything about this. I can't. The risk is too big. Don't worry. I'll give you a quarterly report that tells you exactly what we're doing. And the bank's like, yeah, this report, yeah, how do I know what all these numbers are? Like, where do they come from, right? So they will negotiate a year, 2 years with these banks, and nothing come out of it. So it's very interesting, right? This goes to this other problem, is that what is the cost of trust, right? Is someone measuring the cost of trust, the friction that gets generated in these business deals, as well as the missed opportunity cost of not trusting, the people that you're working with. So I actually asked around, and this is very interesting. This is a rare example where we can actually start to quantify the cost of trust. I found a fund, right, based in Hong Kong that specifically invests in infrastructure projects in Southeast Asia, right? So, well, how are you solving this trust problem? So you know how we solve the trust problem? We hired 180 engineers full-time, and all their job is to fly around the entire world and actually go look at all the infrastructure projects we're investing in, to go read the numbers off the meters, to go talk to the manager every single day. That is the cost of the trust. That's the cost of the trust gap. The hiring, management of 180 highly qualified engineers, right? Plus whatever opportunity cost you might have missed because you just can't trust them. So a similar model could be deployed here as well, right? I mean, first of all, digitize the infrastructure monitoring infrastructure, right? Make these signals, turn them into digital signals, upload them into the cloud, and then anchor them simultaneously, right? Infrastructure projects are actually a lot more complex than video arcade machines because the stakeholders involved there's so many more stakeholders. There's probably like 20 government regulatory agencies, probably 200 contractors are working on these infrastructure at any given moment. Lots of financial institutions and banks who are like desperate to know like where are these numbers coming from, right? So you have lots of parties, lots of stakeholders who have conflicting financial interests, right? And they need some way to reach a certain threshold of trust, right? So trusted devices enable fair business models. I think this is actually a very interesting use case. The second use case. I had actually been very skeptical of this use case for a very, very, very long time. So we're working with a very large industrial conglomerate in Japan to help them gain more transparency in their overseas international supply chain. To be very honest, for the first year and a half of that I was in this blockchain industry, I always thought the supply chain use cases, not interesting, or it doesn't sound reasonable, right? So here are open standards to encourage collaboration. Here what we're really saying is that we're using blockchain as a way to develop an open standard, right? So no matter how strong you are, how much leverage you have on a supply chain, say you're Apple or you're Walmart, right? You can't actually exactly force everyone to get on a centralized system. It's incredibly difficult, right? You think they can because they're so powerful, right? If you don't get on the system, just don't do business with us, right? Well, that's not really how it works, right? Because they're dealing with contractors and suppliers that are like 5, 6, 7 degrees removed from them, that are involving lots of other businesses that have nothing to do with them, right? So it's very difficult to force people to get on a centralized system. And it's also extremely difficult for one entity such as Walmart to build their own system that covers tens of thousands of suppliers all across the world. So very difficult to get them on a system, very, very, very difficult to build the system yourself. It's very costly. So what's a good solution, right? Well, you can propose an open standard, right? You say that here are sort of data standards I need at every step of the way along the distribution chain. You don't have to be exactly abiding these standards. You don't have to be exactly, right? But just make sure that it's something like this, right? What this actually does is that's very interesting. It turns into one single gigantic problem of a single person along the supply chain building a huge system that fits every single person into a lot of smaller problems, right? Lots and lots of tiny little problems in which every little player along the supply chain is responsible for developing their own system according to an open standard. Why do people fight standard wars, right? So this is the thing in IoT is that never ever try to set a standard because you'll lose, right? Or just prepare to pay a lot of money over decades of time and not get anywhere. Well, standards, people fight over standards because they're not fighting over standards, they're fighting over royalties and intellectual property, right? Because whoever gets you set the standard gets to collect royalty from everyone. But if the standard is open, there's nothing to fight about, right? It's just practical business. You turn a centralized, huge problem into many, many, many smaller, localized, smaller problems, in which the pressure to abide by these standards will come from the people that are immediately working with each other, instead of someone who's very far away, right? So this is actually something that we find very exciting, not a short-term problem. This is a very, very long-term thing that you have to get a lot of people on board with. We're working with the largest automotive manufacturer in Japan to actually help them with exploring data democratization. So this is very interesting. So in Japan, the government is pushing all large corporations to start building data banks because if you talk to any business executive or government official in Japan, they're very cognizant of the fact that they pretty much missed out on this whole internet thing. It just didn't happen in Japan, right? So they said we need to catch up. Data is the new fuel. We got to get more data, right? So okay, everyone's going to build data banks, but at the same time, we're also seeing backlashes, right, against data privacy, data ownership. The laws are not here today, but they will be here at some point. So a lot of these centralized data aggregation business models are going to be non-viable in the future. Is it going to be 5 years or 10 years? We don't know, right? But this OEM is extremely interested in building something that is future-proof, right? That is regulatorily compliant for something that might happen in the future, right? So that's something that we're really helping them to do to make sure that we can have a mobility data market that is not going to get shut down in 10 years' time when these privacy regulations do actually come in place. Okay. this is another very, very interesting thing, and probably is very actually unique to the Japanese market. So cooperation. I thought I made up that word. I googled it. It actually exists. So it's competitors collaborating. Okay. This is actually a very, very interesting concept. So in Japan, almost every single industry, almost every single vertical that you see is highly fragmented, right? They don't have this naturally centralizing force that you see in the US or in other places around the world. There are many reasons for that. I think one of the primary reasons why is that most of the financial assets or economic assets are owned, for example, in the US, they're controlled by financial institutions. Okay, banks, funds, whatever. Like anything that, big brands, big industries, they're probably owned by some big fund. Okay, and these financial institutions, they make decisions based on the bottom line, right? Does it make me more money? The stock market like what I'm doing if I merge these things together and create synergy, right? And usually the answer is yes, and if it's yes, they're going to do it, right? It's very rational. Most of the assets, the vast majority of assets in Japan are not owned by financial institutions. They're owned by families, passed down generations and generations, and they refuse to consolidate because there's a lot of emotional value attached to these businesses. So in every single industry you have tons of fragmentation, right? This is also the case in parking. It's very interesting, parking management, right? So just in the city of Tokyo alone, there's probably like 200 parking management companies, right? Just lots of them. Right, so as somebody who owns parking inventory, if you're a real estate developer, if you're a guy who owns a convenience store with 2 parking lots behind your back door, you will naturally want to be able to list your inventory on lots and lots of different platforms. But you can't. You can only pick one, right? If you list on 2, they're not synchronized, right? One gets rented here, the other guy doesn't know about it. Not really great for customer experience. There have been people who came around and said, hey, how about I create a centralized platform and all you guys just give all your data to me. We can synchronize it here. And they're like, do you think we're idiots, right? We're going to give you all my data and you're just going to own us, right, within the span of a year. So they do not consolidate and they don't work together, right? So this creates bad customer experience on both sides. It's a two-sided market. Bad customer experience for people who own the inventory and bad customer experience on the driver's side. Are you really going to install 30 parking apps on your phone for one city? No, and as a consequence, no one just installs any app, right? This just doesn't work, right? So once again, we through another very interesting avenue, right? We actually figured out that we can drastically raise their asset utilization and return on investment by placing magnetic sensors on these parking spots and help them be more intelligent about how they allocate their assets. So most of their inventory is locked into long-term leasing. I can tell you a lot more about how that works. But the first proposal, value proposition walking through the door to these parking operators I'm working with is not, let me tell you about blockchain, because then they'll freak out. Right? Well, this is blockchain, never heard of. I walk in the door and I say, let me tell you how I can make you more money. No, that they don't hear, right? So I have a really good excuse, help them make more money, and get all these sensors deployed across their inventory. And once those sensors are deployed, they start sending signals into the blockchain. And I can say, hey, would you like to make your business much, much bigger? Right? How would you like to do that, right? So you can actually get lots of different players to anchor their signals onto the blockchain and create a decentralized shared scheduling system, worker groups. But if it really wanted to trick a subset of phone nodes, it could. I could totally do that. You could create alternative realities and just trick the light node into believing whatever it wants to believe. So we actually want to build a mechanism that allows the light node to pull a random subset of the network, right? And it's an option. The light node can say use this option or don't use the option, right? Periodically can say, hey, this phone node that's talking to me that I have a business relationship with, is it telling me the truth, right? Do a random subset of other phone nodes on the network agree with me, right? So this is something that we actually really want to build in. There's some more research where we actually are thinking about whether or not it's possible to have what we call localized consensus. Happy to talk about that later. This is just ideas in our head right now, but if someone is interested in that topic of how potentially nodes can not have the full view of the entire state, but still be able to say something with localized confidence that about certain transactions. Maybe you can pull those partial sort of probabilistic consensus confidence into something that's bigger. We're not really sure how doable that is. Love to hear from what you guys think. All right, so this is sort of the end of my talk. This is our Twitter. If you find anything remotely interesting what I just said, or if you think I'm full of shit, go on Twitter, tell me about it, okay? So, thank you.
Thank you, Stephen. So I think Stephen's speech can help us to have a general understanding about Taraxa project. And feel free to ask him any questions during the panel discussion and also after that, since we want this meetup to be a very conversational exchange. So that feel free to ask your questions after each speech. So now let's welcome our honorable speaker, Professor Maurice Herlihy. He's an advisor of Taraxa, Algorand, and many other very great projects. And he's also M1 professor of computer science at Brown University. So Professor Maurice Herlihy has an AV in mathematics from Harvard University and a PhD, especially in computer science from MIT. He has served on the faculty of Carnegie Mellon University on the staff of DEC Cambridge Research Lab, and is currently a professor in the computer science department at Brown University. Welcome.
Okay, so this is a boiled down version of a technical talk, which has probably simultaneously too much and not enough technical material. So don't hesitate to ask any questions if I say something that's overly provocative. This is adapted from a paper that published a couple years ago. That's me. As you know, blockchain is nothing but a distributed ledger. So a ledger is actually an invention of the Italian Renaissance. They invented double-entry bookkeeping. The idea is that you have an append-only list of events that happen. You're not allowed to go back and erase things. You can only add new things. If you do something wrong, you can post a correction, but you can't go back and book the books in some sense. Physically, it looks something like this. We have a sequence of blocks. Each block has a transaction. You kind of distill this and flatten it, and that gives you the ledger. I'm not going to go into details on this because I don't have time, and I assume most of you probably know this stuff anyway. One of the things that, or the thing that I'm going to focus on here are the notion of smart contracts. Now, the thing about smart contracts is they're scripts. They're simple programs that run on the blockchain. They're not contracts by any stretch of the imagination, and they're not particularly smart. The smartest thing about them is the kind of marketing hype that went into the name. But they're still very interesting and very useful features. So again, as you probably know, miners basically assemble blocks by taking all the contracts, all the calls to these scripts, and lining them up. And you run them one at a time to compute the new state. So I'm say an Ethereum miner. I pull calls off of the peer-to-peer network, I line them up, and I execute them one by one. And each of these gives you a new state. So there's kind of a event-state duality here. Each event carries the state from one state to the next one. So you create a block which has the new state and the sequence of contracts that led you to this state from the previous state. You do consensus, which I won't go into. And then at the end of consensus, somebody gets to decide, okay, this block is now going to be the next block. And it gets stuck onto the end of the blockchain, or the beginning of the blockchain, depending on your point of view. Now, of course, nobody trusts anybody in this universe. So if you want to check that something is true, or you want to start up a new node, you have to go back and replay all of these contracts. So in Ethereum, which doesn't have finality, every contract is executed by everyone basically all the time. So the validators replay the contracts to make sure that they were executed correctly the first time. And validators replay all of them in order. You know, if you want to start a new node and you want to really do it right, you've got to go back and re-execute every contract. In real life, people take shortcuts, but this is the way you're supposed to do it. So, for how long are your contracts re-executed? If you write an inefficient contract, how much of an offense is that? You know, at what point will this be forgotten? Well, the answer is you have to execute contracts forever, because you're never going to. It's never going to be the case that somebody isn't going to need to re-execute this. And the subject of our paper is it's bad enough that they're executed forever, but they're executed forever sequentially. That is, they have to be done in a one-by-one order. You line up the contracts, you do them one at a time. You don't get to do them with any kind of parallelism. So the miners execute the blocks contracts sequentially. That might be okay because they're paid by the step. You know, if you win, the consensus that you get paid. If you don't get paid. You know, so that's slightly mitigated. One observation is that if you could figure out a way to do these in parallel, that would give you a competitive advantage, because you could prepare blocks faster than anyone else and start doing your consensus faster than anyone else. So sometimes some people look at me and say, well, you talk about sequential execution as if it's a bad thing. You know, we love sequential execution. It's easy to write programs that way. What's wrong with doing things sequentially? Well, you get poor throughput, again, because you're doing things only one at a time order. Again, it's a competitive disadvantage, because if somebody else figures out how to do it in parallel, they can sneak in front of you. And mostly, you know, every device that you buy these days is a multi-core device. You know, your toaster probably has more than one processor in it. So designing a technology that is inherently incapable of taking advantage of all this free parallelism is kind of dysfunctional. Also, you know, clock speeds aren't increasing, although parallelism is increasing, so you're kind of passing up the chance to surf on the technology wave by making things sequential this way. So what can we do? Well, the simplest thing you can do is say, okay, well, let's just execute these things in parallel. Why don't we just line up each of the contract calls, hand each one to a core, and let them all run in parallel. So that's obviously a bad idea. Anybody want to come up with a one-word reason why that's a bad idea?
Dependencies.
Big one?
Dependencies.
Yeah. And that's because the contracts have a shared state. And if you run them in parallel, they'll mess each other up. So you can't just run free market concurrency without any kind of regulation, because you'll end up with an inconsistent state and bad things will happen. And people can exploit this, because after all, these contracts manage money. And every hacker in every cafe in large parts of the world is sitting around looking at your code, trying to figure out how to do a life-transforming event by stealing all your money. So that would make double spending relatively easy if you could do that. You could add explicit concurrency to the programming language. You know, this is good because I could sell more books on how to write concurrent programs. But really, that's not a great idea. Writing contracts is hard enough as it is. You know, I teach an undergraduate blockchain course at Brown, and I have 3 weeks of lectures of Solidity exploits and bugs. And it ranges all the way from low cunning to really profound insights. It's mostly low cunning. But a lot of them are concurrency bugs in disguise. So next thing you can do is you can say, well, so I can't just run any old contracts in parallel, because some of them have dependencies. Most of them probably don't. It's hopeless to try to ask the people who write the contracts to tell us about it because they have enough troubles as it is. We don't want to make things worse. So how about we just get a really smart compiler or analyzer and look at the contracts and say, okay, so these contracts here can run in a parallel, and these can't, so schedule them in that order. No, that doesn't really work either. So it's undecidable in theory, which is actually not so important because we do undecidable things all the time in practice, like compiler optimization. But it turns out, particularly for Ethereum contracts, that this doesn't really work out very well. But because contracts can call other contracts in most of these languages, in Ethereum you can have you have the equivalent of function pointers. So I can change a pointer to point from one contract to another contract dynamically, and so the call graph is dynamic, and in the end everything looks like it depends on everything else. So static analysis, even conservative static analysis, isn't very promising here. So this is how we're going to do this. We're going to take Grace Murray Hopper's famous observation that it's often easier to ask permission, it's often easier to apologize than to ask permission. So what we're going to do is we're going to go back and execute these contracts in parallel as quickly as we can, but we're going to be careful about it, and if we detect that there was a conflict, then we halt one of them and we roll it back. So we're going to speculatively execute them in as parallel a way as we can. And if it's true that hardly any contracts conflict with each other, then we'll win. And if it turns out that there is a lot of conflict, then we lose, but then there wasn't any concurrency to be had anyway. So that's not so bad either. I once gave, when I was my first year as an assistant professor at Carnegie Mellon, I chauffeured Grace Murray Hopper to the Pittsburgh airport from CMU, my one brush with greatness. So speculation, so we're going to execute transactions in parallel without asking permission, but we're going to instrument the memory to detect conflicts. So every time you read or write, you set a little bit somewhere, and if we detect that there's concurrent activity, then boom, we stop things. And we fix things when conflicts are detected. And the actual mechanisms for doing this are the fun part, and I don't really have time to go into this in detail. But basically, we keep undo logs and we put sort of tripwires on memory. And so what happens is we'll run a contract. We'll detect, oh, sorry, this contract conflicted with someone else. We'll stop it dead in its tracks, roll back any intermediate results, and then schedule it later. So we originally had a fairly elaborate scheme where we would build a fork join schedule, and you could prove all kinds of nice theorems about this. But it turns out that we can be much more pragmatic. So the idea is when I finish a transaction in this wild parallel speculative phase, I'll put it in one bin and say these are the committed transactions. If I run into a problem and I have to roll back a transaction, then I'll put it in the second bin and say, sorry, this one is a troublemaker. This one has a conflict with the committed transaction. Of course, the choice of what's in what is non-deterministic. And so after I finish running as many as I can in parallel, then I'll take the ones that had conflicts and then I'll run them sequentially. Now, it's possible to say, well, I could do the whole thing over again and try to run the losers concurrently again and see what happens, but it turns out that doesn't really pay off. That typically, if there's conflict, it's usually conflict on a small number of locations. So trying to run the remainder in parallel doesn't really work very well. So any kind of speculative execution depends on an assumption that conflict is rare enough. And so the question is, how can we justify this claim? Well, blockchains have this highly unusual feature, which everyone knows about, but nobody's really noticed, is that you have a complete history of everything that ever happened during the lifetime of the blockchain. So if I want to claim most concurrent smart contract calls don't interfere with each other, I can go back and look and see whether that's true by looking at the actual blockchain. Now, the actual Ethereum blockchain is pretty humongous, so you want to sample things. So we wrote another paper, and my co-author is sitting here in the front row, Vikram. He's here to make sure that I tell the truth. And so the question, so speculation works best if there are few dependencies and conflicts. How many conflicts are there actually? If only there was a way to observe past transactions. Oh wait. So what if we take this two-bin speculative idea and we go back in time and we look at all of the transactions that were actually submitted to the Ethereum blockchain at some point in the past, and say what would happen if we were to take those transactions and rerun them using our shiny new device. So we didn't run everything because it would still be going on if we did. So we sampled the blocks, we executed them concurrently, and then measured how much we would win. And here too, like we give an entire talk about the methodology, how we measure concurrency, how we do this, that, and the other thing. There's a paper out there if you want to get into the really gnarly details. I'm going to skim over things here. So basically what we did was we picked a few times over the lifetime of Ethereum and sampled those. They're evenly spaced. The blue line is basically how much traffic there was at the time. So we picked 7 historical periods. 1 week long, separated by 11 weeks. This was after the DAO disaster, after the hard fork following DAO, but before CryptoKitties really made life difficult on Ethereum. Again, I don't have time to really go into these in a great detail, but pretty much what you can see here is that in the beginning there were lots of opportunities for concurrency. You get 8 and 9-fold speed up. As time went on, the opportunities for concurrency went down, probably because of ICOs and the start of things like CryptoKitties. So there were some things that there were some events that caused a lot of contention. And so you can see that the conflict level goes up and the sort of speed up goes somewhat down. We measured hotspots. Where did these conflicts happen? They mostly happened at fairly small number of places. The actual story is somewhat complicated, but that's the kind of the one-line summary. Things that we tried that works. Distinguishing between reads and writes turns out to be important. So if all you do is you look at memory accesses and you say any 2 memory accesses to the same place are a conflict, then you don't get much concurrency, because it turns out that a lot of contracts read random stuff for reasons we can't quite figure out. But if you recognize that concurrent reads to the same location are not conflicts, then that's a really good thing. That's effective. If you go in, and CryptoKitties here stands for small number of high contention events, like hot ICOs and actual CryptoKitties. If you look at the contracts calls that don't involve a small number of highly contended events, then this technique still does pretty well. So it says that there's a small number of hotspots that really gum up the works, but that most of the rest are pretty low conflict rate. You can also just drop the 5 most contended contracts. In order to check that our methodology was sound, we tried doing finer rates of sampling over small intervals where we would just take every transaction. And that turned out not to have any effect on the numbers. So we're reasonably confident that our sampling techniques are right. As I said, we had 2 bins. We have one for the concurrent calls and one for the non-concurrent calls that we ran sequentially. If we kind of recursively tried to winnow through the second bin, that didn't really pay off. Again, because the ones that conflicted tended to conflict on a very small number of locations. We tried measuring concurrency by gas and by instructions, and the curves end up looking pretty much the same. So that's another methodological question. We tried doing static prediction, where we look at a program and try to figure out ahead of time, is this a candidate for concurrency, and we would bin it if it didn't look promising. And it turns out that it didn't really have much impact. So I'll leave you with a conjecture, which is something that we're actually working on. This is Fermat's famous conjecture in the background. So most conflicts are probably conflicts on account balances, meaning that I want to buy an ICO token, I bump a counter from 99 to 100. And you want to buy a same token, you bump the counter from 100 to 101. Now, these operations actually commute. There really isn't any conflict, because it doesn't matter what order we do those in. Now, when we look at how the Ethereum virtual machine works, and remember, all we can see is the bytecode. We can't see the original source code. We suspect that a lot of these conflicts are reading a variable, incrementing it, writing it back, which looks like a read-write conflict to us. And it causes us to throw up our hands and roll back one of the transactions. In fact, with a more sophisticated analysis, we could probably have let them run in parallel. And so our conjecture is that this is the source of a lot of the problems. Addition and subtraction commute except for underflow and overflow, which are probably reasonably rare. So what if we had, for example, an Ethereum virtual machine that had atomic counters as a built-in primitive? So we could recognize this from the bytecode. There's some prospects for looking at the bytecode and doing pattern matching and saying, oh, this is really just an atomic increment. We increment the value, but we never look at it. It turns out that's tricky, but probably not impossible. What if we had zero knowledge conditional? Zero knowledge conditional will do a comparison and branch one way or the other, but not give you any information about what you saw. That would, in combination with atomic counters, that could give you a lot of concurrency in places where currently we can't see it. So the conjecture is that there's a lot more concurrency hiding in these smart contracts if we had kind of a more sophisticated analysis. We just did kind of the simplest. The low rate of conflict was valid, and what we discovered was actually more complex and more interesting than we anticipated. We thought either everything would be highly concurrent or that nothing would be concurrent because everyone is reading some performance counter somewhere. But the truth turns out to be more interesting and more complicated than that. Okay, so that's all I have to say. I'm happy to take questions. Yes?
Was the state maintained for a processor or for a bit?
So we had a we had a shared memory that was instrumented. So every time a thread would write, a thread executing contract would write to a location, we would check and see is there a bit set that says that this is a dirty. You can think of it as a lock. Is someone holding the lock? If someone has the lock, then we say conflict and bail out. Yes.
Are there any rules on how far you can roll back?
You roll back to the beginning of the contract. So everything that the contract did, we basically keep an undo log. And then if we say, oh, there's a problem, then we go back and undo everything that it did. And it turns out that that's okay. If you went through and did a bunch of steps without conflicts, then it's safe to roll back. You won't harm anyone else, because anyone who came after you would be rolled back themselves.
Would you read? So then would you roll forward?
Then you take the transaction and you say, okay, we'll run it sequentially later. So we have a whole bunch of concurrent transactions, and then the stragglers we just run one at a time without trying to be clever. Yeah.
Did it also occur that the aborted transactions just never made it to any block?
No, we since we're kind of simulating and replaying these things, we can do anything we want. So we just ran them sequentially and said, if we'd done this in real life, with this strategy, then it probably would have come out this way. We didn't, in practice, it might be that we ran them in different orders, then a later transaction would have taken a different branch and done something different. We didn't really try to capture that level. We assumed that over these millions of different executions, that kind of thing wouldn't really have an effect.
So do you have a solution for that in a real life scenario?
Oh, so we don't have a concurrent EVM implementation. The same way there's a concurrent JVM implementation. If we had, we could have done better experiments. The reason we did things this way was we didn't feel we had the resources to do our own concurrent EVM. Nobody else seemed to have done it for us. And so this was the next best thing.
Yeah, just to chime in, we've implemented everything actually. So we do have a concurrent EVM, but we're also getting the same results as from Press Herlihy as predicted. So we are also going through the interesting more things that we could do, right? So we are making progress on that.
Any more questions? Okay, so I'll pass it on to the next.
So we'll start